This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to talk about heat transfer, specifically conduction, convection, and radiation. Now, we've been talking about heat for the last few videos. Specifically, we've talked about the fact that to raise the temperature of an object by an amount delta T, I need to add an amount of heat Q, where Q is equal to the mass of the object that I'm trying to change the temperature of, times its specific heat capacity, times delta T, the change in temperature that I want that object to undergo. So that's one example of heat that we've talked about. One of the other things that we've discussed is that it takes heat to change the phase of a material. So the amount of heat required to change from a solid to a liquid, that's the heat of fusion times the mass that we're trying to change. And to change from a liquid to a gas, the amount of heat required is the heat of vaporization times the mass of the liquid that we're starting with. So that's what we've talked about in previous videos. But now we want to look at specifically what are the ways that heat actually gets transferred. And it turns out that there are three of them, which you may have heard of before: conduction, convection, and radiation. And we're going to go through all of these. You'll notice that convection has something to do with the fact that hot air rises, something that you're probably familiar with. So that putting my hands over a hot fire, I feel that heat transfer, and that has to do with the hot air rising from the fire. You also, I'm sure, have had some experience where you've had a metal object contacting something hot. So for example, we put this hot poker in the fire, and we know that we want to have a glove on our hand because that heat is going to transfer right up that metal object, and if we didn't have the glove on, would transfer right to our hand. Radiation is maybe the hardest to understand, and that is, even if I have a glass window in front of my fireplace, if I put my hands out, I still feel that heat. Well, that's certainly not from conduction, and it's also not from convection, and that's radiation. So that's the hardest one to understand, and so that's the one we're going to start with. So did you know that right now you are glowing like a light bulb? So you might wonder, what do I mean by that? We know that a light bulb, when we turn it on, gives off light. And we're going to call that visible radiation. So light is an example of radiation. But what you might not know is that you and I are also giving off radiation right now. But we give off something called infrared radiation. And that's not visible to the human eye. So it's not visible, but we are radiating in the exact same way that a light bulb is, and we'll talk much more about that. It turns out, though, that to understand this concept of radiation, we have to talk a little bit about what we mean by a wave. Now, in this course, we're going to talk a lot more about waves because we already know that when you're doing ultrasound, you're using sound waves. So we've got to have a very good understanding of waves in general. And this is going to be our first introduction to waves, but we'll come back at this in a few videos and really get into it in more depth. But for right now, we want to just understand, what is a wave? Well, a wave is a vibration that travels through space. And I don't know if you've ever been at a gym where they have these big heavy ropes that you can shake up and down, as our person is doing in this picture. So as she shakes the rope up and down, as she vibrates that rope back and forth, you can see that a wave pattern is forming on the rope. And so here's kind of a slightly more scientific looking diagram of the same thing. We've got a man here, and he's shaking that string, And you'll notice what he's doing is he's shaking that string up and down. And as he shakes that up and down, what forms on the string is a wave, and the wave travels in this direction. So that would be the direction of travel. So a vibration is a wave that a wave is a vibration that travels through space. Let's talk a little bit more about this. There's one other key concept that we need to understand radiation in terms of heat transfer. And that is, we need to understand what we mean by the frequency of a wave. Well, the frequency of a wave is simply the number of vibrations per second. In other words, how many times per second does our person shake that rope up and down? And you can imagine if he does it, just a few times up and down per second, that would be a low frequency wave. And so you'll notice the peaks would be farther apart as that wave travels away. You can imagine he could shake it really fast up and down, and that would create a high frequency wave. And so a high frequency wave would look like this, where the peaks are going to be closer together. And again, we're going to talk much more about this, and we'll go into it in a lot of depth in a later video. But right now, that's kind of the basic stuff that we need to understand about waves. That vibrations create waves, so a wave is just a traveling vibration, and that if we vibrate, in this case the string up and down quickly, that's a high frequency. If we do it slowly, it's a low frequency. So now we're really ready to understand what we mean by the term radiation. It turns out that what we mean by radiation is we mean electromagnetic waves. So what do we mean by electromagnetic waves? Well, you can probably recognize the words that are in here. It's basically a combination of electricity and magnetism. And again, we'll talk more about this later in the course. But an electromagnetic wave is oscillating electric and magnetic fields. And it turns out that's what visible light is. So your eyes can see electromagnetic waves. But electromagnetic waves are more than just visible light. Look at all these terms that you've heard before: radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Well, those are all the same thing as visible light. The only thing that differentiates a radio wave from an X-ray, from visible light, from gamma rays, is the frequency. And so in this chart right here, you'll notice we have a plot, and what they're showing here is the frequency. And so as we move to the right, the frequency is higher. You'll notice that visible light is right in the middle. And by the way, we call this the electromagnetic spectrum. So the electromagnetic spectrum, which simply means all the different types of electromagnetic waves. And so radio waves, like are used to broadcast, radio and TV, microwaves, which are used both for cell phone communication but also in your microwave oven, they're lower frequency. Then we get up to infrared, which is the next highest. Then we get to visible light. And what I want you to notice is visible light is a very narrow part of the electromagnetic spectrum. What makes it interesting to us is simply that that's the little bit of the entire spectrum that our eyes can see. And the reason, in fact, that our eyes evolved to see that part of the electromagnetic spectrum is that's where the sun radiates most of its energy. We'll come back to that. Then above that, ultraviolet, X-rays, and finally gamma rays. So as we move to the right here, we have higher and higher frequencies. So it turns out that every object that's at a temperature above absolute zero, which basically is every object, emits thermal radiation. And that's why I say that not only does a light bulb emit thermal radiation, but so do you and so do I. And the key thing about the radiation that's emitted is the frequency of the radiation is proportional to the temperature. So the higher the temperature of the object is, then the higher frequency electromagnetic waves or electromagnetic radiation is emitted. So objects like you and me, we're not that hot, so we emit in the infrared part of the spectrum. But something like the filament in a light bulb is hotter, and therefore it emits at a higher frequency. Now, if you've ever played with a dimmer and a old-fashioned light bulb on a dimmer switch, I don't know if you've ever noticed this, but just as you're turning the bulb up when it first begins to give off visible light, you'll notice that it looks red. That's because it's just emitting light in the red part of the visible light of the spectrum of visible light. But then as it gets hotter, it starts emitting across all of the colors. And when something emits across all of those colors, that's what we see as white light. So white light is simply the combination of all the different colors of the visible part of the spectrum. So again, red light is at a lower frequency compared to violet light. And kind of yellow-green is right in the middle. So you and I, we emit infrared. You'll notice if you've ever seen a piece of metal heated up, you'll notice it starts to glow red first and then it starts to glow white. If it keeps getting heated up even hotter, it will start to get kind of a bluish tinge as it's starting to move more into that part of the spectrum. So that's the key. The frequency that's emitted is proportional to the temperature. Now, objects don't just emit radiation, they also absorb radiation. So every object both emits and absorbs radiation. But as you can imagine, if the object is hotter than its surroundings, for example, the fire in this fireplace, it's going to emit more energy than it will absorb. If an object is cooler, so in this case your hands, they're going to absorb more energy than they emit. And another way we've kind of said that earlier in the course is we've said that heat flows from higher temperature to lower temperature, or from hot to cold. And so this is just an example of that. So a little check question here. How does energy from the sun get to the earth? Well, I think you probably all know the answer to this, and that is it's simply radiation. So again, radiation, or what we call electromagnetic waves, are what the sun puts out, and much of what the sun puts out is in the visible part of the spectrum. That's why when you look at the sun, obviously you can't look right at it, but it's basically a big white ball, and that's because it's putting out most of its energy in the visible part of the spectrum. But it does emit in really across the entire spectrum, just mostly in the visible part. Okay, so if it weren't for radiation, we wouldn't be here because the Earth wouldn't be able to get energy from the sun. The next way that heat gets transferred that we want to talk about is conduction. And so let's start with this question. What do you notice when you stir hot soup with a metal spoon versus a plastic or a wooden spoon? Have you ever been stirring something hot with a metal spoon and you forget and you leave the spoon in the pot, and then you come back and it's too hot to touch? Whereas if you're using a wood spoon or a plastic spoon, you don't have the same issue. And so this is all about conduction. What do we mean by conduction? We really mean two different things. When we talk about heat transfer via conduction, we can mean either the direct contact of two objects. So for example, if you put your hand on the desk, it will probably feel cool because heat is being conducted from your hand to the desk or to the table. But we also mean transfer within an object. So for example, let's say that I took a lighter and I held it up under one end of the spoon. As the spoon gets hot down here, that heat will transfer throughout the spoon, and the entire spoon will get hot if I hold that lighter on long enough. So metals are very good conductors of heat. The reason that a metal is a good conductor of heat has to do with the fact that the electrons in metals, the outer electrons of the atoms that make up a metal, are pretty much free to move around. They're not tightly bound to any particular atom within the metal. And so as I heat one end of the spoon, you can imagine the little electrons that are pretty free to move in there. They start moving a lot because they're absorbing that thermal energy, that heat, and that's giving them kinetic energy. Because those electrons are free to move around, they start moving throughout the entire spoon, and that's how the energy gets transferred or conducted within the spoon. So that's what makes metals very good conductors. That also, by the way, is why metals are good conductors of electricity, because those same electrons can carry an electric current, and we'll talk about that more in a later video. We also know that there are lots of materials that are good insulators. So we've already talked about wood and plastic, but you can imagine things like glass or styrofoam, air. Those are all good insulators. What makes a material a good insulator is that the electrons are bound to each individual atom. So there are not a bunch of free electrons. And therefore, when I take a wood spoon, even if I heat up this end, there's no way for that heat to be conducted through the material, because unlike in the metal spoon, all the electrons are tightly bound to the individual atoms, and the atoms are stuck in the structure of the material. So there's really nothing that can easily transfer the energy throughout that insulated object. And that's also why you can't use something like wood or glass or plastic to conduct electricity, because we can't get a movement of electrons through that material. The last method of heat transfer that we want to talk about is convection. And convection refers to heat transfer because of the movement of liquids or gases. Remember that we can talk about liquids and gases together by referring to them as fluids. So a fluid can be either a liquid or a gas. And we get convection in fluids, so both in liquids and gases. So what happens in convection is that the molecules or atoms that make up the substance start to absorb energy and move faster, and therefore they spread out and become less dense. And so we know that something that's less dense is going to rise relative to something that's more dense. When a liquid or a gas cools, it becomes more dense and sinks. So let's look at some examples that illustrate this. This is kind of an interesting one. Here we have a room and we have a radiator. You'll notice that there's no fan involved with an old-fashioned radiator like this. So how is it that that radiator can heat up an entire room? Well, it wouldn't work except for convection, because here's what happens. The air above the radiator gets hot, and so that air begins to rise. But as that air reaches the ceiling, it really kind of has nowhere to go, so it starts going sideways as more hot air is coming up. But now as that air moves away from the radiator, it begins to get cool. And so it begins to fall or sink down. And what happens then is we get this natural movement of the air around a room. So the hot air rises up. As it moves across the room, it starts losing energy and cools off, comes back down, and then comes back to the radiator and gets heated again. And so that's how we can have a radiator in just one corner of a room and have it heat the whole room. That's by convection. Another example that you're familiar with is when you see boiling water. That's another good example of convection. In other words, the bottom of the pot is being heated by conduction. So either the flame that's being shown here, like on a gas stove, or sitting on the heating element in a metal stove. We conduct heat to the bottom of the pan, which conducts it to the water that's in the bottom of the pan. But now that water that's in the bottom of the pan becomes hot. And as it becomes hot, it becomes less dense, and it rises up. Well, now water that's up at the top has been cooling off, and so that comes back down. And that's why we get that chaotic up and down motion when we're boiling water. That's an example of convection. So let's review the three back to this initial diagram that I showed you. Again, convection has to do with fluids, meaning gases and liquids. As they become hot, they become less dense, so they rise. Therefore, if you put your hands directly over a fire like this, you feel that heat because of the rising hot air coming from the fire. Conduction can be within one object or from one object to another. And again, in this case, the poker here that's in this part of the fire is getting very hot. And what that means is the electrons in that piece of metal are beginning to move very fast. They can move along the metal, and that's what conducts the energy and begins to heat up the rest of the poker. Again, if you didn't have a glove on here, it would transfer that heat via conduction to your hand and potentially burn you. And then finally, we have radiation, which is the electromagnetic waves being given off due to the temperature of this object. Again, even if we put glass here, so we're definitely not getting heat by convection or conduction. You put your hands in front of the glass, they still feel hot because the radiation, as we know from visible light, goes right through the glass. Let's end with this final example, which is how does a thermos work? So if you think about what you're trying to do with a thermos, you're trying to either keep something hot, hot, or something cold, cold. And we know that heat can be transferred three different ways: conduction, convection, and radiation. So if we want to stop that, we've got to stop all three. If you open up a thermos, you'll notice that the walls are silver. And the reason that they're silver is because we know that light will reflect off a silver surface. In other words, when you look at a mirror, you see yourself because the light is reflecting. So that means we can both keep radiation out, but also radiation that's inside the thermos. If we're storing something that's hot, it's going to reflect back off that silvered wall and stay within the thermos. So that's how we keep the radiation in. We put a silver coating on the inside. In terms of conduction and convection, what we do is we create a vacuum. And so lots of thermoses now are made of metal, but they still have a vacuum. In the old days, they used to be glass. But the idea is we suck all the air out of the inside there. So we have basically a double wall, and in between the two walls, there's a vacuum. And therefore, even though heat can get to this metal layer, it can't get through the vacuum to the inside. And so both there's no motion, so convection doesn't work, and conduction doesn't work. Okay, so that's the end of this video. In our next video, we'll be moving on to talking about fluids.